as the official discussant of the TOC community, I've been asked to share some of my thoughts in the next 15 minutes about multiple hypothesis testing. And this is we looked into it with some of the people here and otherwise, based on some intriguing similarity that Cynthia pointed out between the error accumulation in multiple hypothesis testing and the way privacy errors can accumulate when you're querying a database multiple times. But the literature was so beautiful that we allowed ourselves to forget at times the original motivation. But even with this kind of very superficial reading into this literature, I'm certainly not an expert. So what these 15 minutes are going to be about, I suppose that you are not interested in reading my Dear Diary entries about reading your papers, especially you have. But the point, I guess, of this program and this workshop, the observation is that more and more statistics and CS are kind of overlapping. And therefore, it could be useful to go over some of the raw thoughts and even misunderstandings of a computer scientist reading this literature. I should say that before, while preparing it, I was afraid of two things. One is to kind of bore the statisticians by raising things that they already discussed and settled in statistics kindergarten. And the other thing was to be just wrong. I want to claim that all of this can be embarrassing for me, but I think it can still, even in this case, can still promote science. And anyway, I think that compared to the errors that Yoav was pointing in textbooks in statistics, I may not do worse. Again, I won't give references because of the time and also not to get them wrong. But in our defense, I would say that we started 20 years behind, and by now we're raising ideas that are only 2 years late. So if you want to understand what or guess what you're going to publish in a year, ask us in 3 years, we'll know. And the plan is to discuss kind of these three kind of ideas. They are mainly about what are the definitions or kind of frameworks that are natural to a computer scientist and perhaps could help merge some of these research fields. And I mean, the talk was so clear, I'm not sure it's needed, but let me just do a very quick recap of one slide. So we have our M null hypotheses, and we're putting our M best scientists on the job, trying to test each one of them. Out of each, the true nulls are M naught. We're getting all of the p-values for each one of these tests. And now we want to select the ones that we think are significant discoveries. These are the ones that we love. So naturally, we'll call them the rejected ones. Because we are, it doesn't make sense at the first reading, but it makes a lot of sense. We are rejecting the null hypothesis, and this is the only thing we can do. And now, just the parameters, we have R, which is the number of rejected. Among them, we have V that are rejected, although they are true nulls, which are the type 1 errors that we want to bound. And we have these two measures that we heard about, the family-wise error, which is just a probability of making any error, any type 1 error. And the other one is what the expected fraction of errors we're making. So think about it as V over R, but if we didn't find anything, we say that the rate of errors is 0. Okay, so I'll start with the most, banal, I think, observation for the statisticians. But this is about parameters. So for a computer scientist like myself, I feel that I'm missing some parameters. And I guess the reason is that I was raised on this valiant pack learning, where we want to learn an hypothesis, an approximation age to some function f, and our measure is that we want the probability of our learning algorithm that this is an epsilon approximation of what we want to learn, that this probability that it will be, that we are not, that it will be more than epsilon, will be smaller than delta. So I can, I can think about this as delta being the statistical significance of my finding, and epsilon being the material significance. And at least in learning theory, I think that separating these two parameters was extremely important and was responsible to some of the most interesting research done. For example, boosting as a way of amplifying one of these parameters. Now, p-values combine these two kinds of errors, and of course, the statistical literature is well aware of it, and we saw some of it in the second part of Yoav's talk. But I'll just say that, I mean, a natural definition for me would kind of separate these parameters and perhaps have p as p. What's the probability of getting this result if the null hypothesis is an epsilon approximation of is epsilon true? And similarly for the FDR, one natural kind of question is, should we talk about the expectation or talk about the probability that the false discovery rate is larger than something? And again, the literature deals with it. I'm just pointing out what's the natural definitions for a computer scientist. Okay, so that was one point. The other point starts with this kind of criticism of FDR that comes with this example. So let's think about a situation where with probability half, we don't find anything. And with probability half, we do find, we do reject something, some hypothesis. And in this case, the expected ratio of our errors is 2 alpha. In this case, the FDR will be alpha. And the criticism says, okay, but the interesting case is the case when we do find something. And therefore, in this case, we have an error rate which is a bit larger than we hoped for. So one can think of FDR as the a priori probability that when we look at one of the rejected hypotheses, it will be truly null. And the question is, can we come up with a posteriori guarantee? So say, given that R is larger than 0, and this is exactly what Story did by suggesting the positive FDR, which is the expected fraction of errors conditioned on R being larger than 0. But I mean, we can suggest a similar criticism of the PFDR as for the FDR, because here is another story. So in this story, with probability half, we have just one finding, and in this case, the finding is correct, always. With probability half, we have 100 findings. And then, in this case, the ratio is 2 alpha. Again, the FDR, and the PFDR will be alpha, but the really interesting case is the one when we have a lot of findings. This is the case where we're going to invest a lot of money later in looking into all these findings. And again, this is a bit larger than the ratio that we were shooting for. Now, as far as I understand, in the Bayesian setting, where each hypothesis is with some probability null and with some probability false, the null is false, then the PFDR does give a good interpretation in terms of posterior probabilities. And the question I'm going to ask is, can we have a similar situation when we don't want to adopt the Bayesian perspective, but want to look at it from a frequentist perspective? So can we, for example, ask for the expectation of the probability of the fraction of errors, the rate of errors, conditioned on all that we've seen, P1 up to Pm? And the answer will be that no. And certainly not in the setting of the original Benjamin-Hochberg study, where we have S, which is the set of true nulls, and for them, the PIs are, even when they are IID and uniform, but we're making no assumption of the other PIs. So in this setting, condition on the P1 up to Pm, there is not a lot of expectation that's left, or probability distribution that's left. So now the question is, what is the right definition for this a posteriori kind of definition? And I'll again come to something that Yoav was talking about in his talk. But from the perspective of kind of testing, property testing, which is thinking about it as a mixture of distributions. And let's concentrate, join the industry that Yoav was talking about of estimating M naught. And instead of just completely finding which are the true nulls and which are not true nulls, but just estimating the number of true nulls. And this does improve Benjamin-Hochberg procedure by itself. So in the setting of independence, what we're seeing is M naught PIs that are uniform in 0, 1. And I'll denote it by uniform 0, 1. And we're seeing some other PIs that are arbitrary. So we have this sequence of specific observation that we have seen. I'm not making any assumption, like in the Benjamin-Hochberg setting, I'm not making any assumption of what they are. But I want to define a distribution X, which is uniform on these values Pj, on these specific observations. And now what I have here is that the sequence P1 up to Pm that I'm seeing of P values, a random element in this sequence is a mixture, is distributed according to a mixture of two probability distributions. One is X, and the other one is the uniform distribution on 0, 1. And the weights are dependent specifically on M naught. So, by the way, if it's not independent, we can do a similar trick with respect to the uniform distribution. So now the problem is very similar to something that both statisticians and computer scientists have been looking at, which is to kind of separate, or at least estimate the weight of a mixture of two distributions. And so we would like an estimator M naught hat, such that first the expectation of M naught at will be larger than M naught. Therefore, we can use it, for example, in the Benjamin-Hochberg procedure. And we want it to be the case that as X gets far from uniform, the estimation gets close to what it should be. And that's natural. The PIs for the non-true nulls is arbitrary. They can be uniform. So if they are uniform, nobody can expect us to estimate M naught well. But if they are different, if there is a difference between true nulls and non-true nulls, we want to get a benefit out of it. And now this is a framework, because now we can ask, what does it mean that X is far from uniform? And we can have various kinds of answers. It can be different in Earth mover distance, in some moments. And given the answer we're giving here, so some assumption on what interests us, we'll get a different way to provably estimate M naught. So this is kind of a framework, and each one of these suggestions would give us an estimator that's always correct and can be useful depending on our input. Okay, and let me go to the third and last point I was trying to make, and the point is that the picture is kind of changing, and it was never always this case of kind of these M scientists coming up with M hypotheses that they want to test and doing this in general, but it's more and more a situation where we have a procedure, an algorithm, a computation that is generating the hypothesis and testing it within kind of as a subroutine of an algorithm, of a computation. And now the errors of individual hypothesis testing is not what we care about. What we care about is the overall error of the procedure. And perhaps as a next stage, we can ask not what's the procedure and what's the error rate of the procedure, but what's the error rate that the task requires. Similar to asking about the efficiency of an algorithm versus the efficiency of a computational problem. I want to say that you can definitely describe both family-wide error rate and FDR as special cases of this more general definition. And let me conclude with asking about adaptive choices of hypotheses. Can we use this, the fact that we have some control about the hypotheses that we're generating, to get things that are better? And indeed, we already saw some of this in the talk. Filtering, where you're doing 2 rounds or more of filtering your hypothesis. This tree kind of approach to testing, pairwise comparisons, model selection, various cases where the hypothesis testing is just a mean to an end. So this is not new, but this framework of suggesting controlling the procedure error could be a useful one, and definitely a useful one by the connection it's making with machine learning that does want to think about things this way. And there is a connection to differential privacy, which was our original motivation. And I'll just say that in differential privacy, error accumulation can be better than linear. And the question is, can we adopt it into the multiple testing? And this could be the case when the hypotheses are related. Finally, adaptive choices of hypotheses have its dangers. We can adaptively go into, especially when we're reusing data, we can adaptively go into the anomalies of our data. And I think CS has something to offer with this respect as well. So in conclusion, there are many connection points between multiple hypothesis testing and theory of computing, both machine learning, differential privacy, property testing. And the perspective may be a bit different, but bridging this gap could be useful. And I want to end with this idea of this question of what can be done with this notion of controlling the procedure error rather than the error in hypothesis testing. That's it. Thank you.
So, any follow-up? Would you like to offer any comment?
Agree to some. I wonder whether the error rates that I didn't discuss give you some, where you talk about assuring that the probability that V over R will not be bigger than 1 minus, will not be bigger than epsilon, to keep this at the probability of alpha.
Right.
Will not give an interesting connection to what you wanted in terms of the 2 error.
Right, right.
That's
definitely.
That might be, might be interesting to explore.
This is just more of a comment or a connection. So this adaptive hypothesis testing motivates a field of active learning, which is a line of research in machine learning, and I think Nina Balkin is going to talk about that tomorrow, and I think Vitaly might be around. They have some more recent work connecting that to privacy.
I was just going to ask if, I mean, one way to state what you're after, if I understood at least one of the things you're after, understood correctly, is basically you want, effectively a confidence interval on this V over R, right?
Right.
That would be one way to when I output a list of hypotheses, and I output also some post hoc, estimation of how good I am, and obviously that's going to require, it might require extra assumptions or more information about the.
I mean, actually, I'm not even sure. I mean, the literature does give, in some cases, margins of errors. I'm not saying that the literature doesn't deal with it. I'm only asking kind of what's the natural basic definition to deal with. I mean, the literature specifically talks at times about margins of errors. So it's less, I mean, my point of view in all of these is less about, completely new ideas, but asking what's the right definition to work with, what's the right framework to work with.
One comment that I'll mention is that you're worrying about the distribution given the p-values. And in fact, the original theorem has a few conditions of the p-values that are not, do not come from the null, that are non-null. You condition on whatever values they have, and you still have the false discovery proportion to expectation. And so it seems strange, but if you just all of your p-values are uniform 0, 1, and you just color them and say this half are false and this half are right, and you do the false discovery and use the procedure, you will get the false discovery rate of a half times q. So in that sense, moving from this situation out is a matter of power more than FDR. So power, discovery rate, false non-discovery rate, and this kind of ideas may be useful for this notion.
Okay, let's thank Omer.